Hi, I'm Ms. Hearn. Let's get started. In this video, we're going to talk about how to apply Euler circuits in real-world problems. But before we get to that, there is some terminology that you need to be familiar with. First, a walk is any route through a graph along a sequence of adjacent vertices. For example, I might go from I to J, and then J to H, and then H to G, then turn around and go back to H, and that would be an example of a walk. A walk can cover any or all of the edges any number of times. The only rule that you can't break with a walk is you can't go off the graph. For example, I can't go from I to J and J to H and then over to F. A trail is a walk with no repeated edges. I to J and J to H and H to G, then G to F. That would be an example of a trail. What I could not do is turn back around and go from F to G and G back to H and repeat a couple of the edges. That would be a walk, but it would not be a trail. It's important to understand that walks and trails can be called by other names, so check with your textbook for your class to see what terminology they use for the same concepts. Another term that we will use is the term closed. A walk or trail is called closed if it begins and ends at the same vertex. Let's take a look at an example. Here we have a walk that goes from F to J, and then to I, and then to H, and then to G, and then back to F. This is an example of a closed walk. Actually, it's also an example of a closed trail because it has no repeated edges. Closed trails are also called circuits very commonly. We will be interested in a very special kind of circuit that visits every edge in a graph. Notice that the circuit we just looked at did not. We were missing the edge HJ, so this is not what we call an Euler circuit. Here's an example of an Euler circuit. We go from A to B, and then to C, and then to D, and then to E, and then to C, and then back to A again. It's closed. It begins and ends at the same vertex, A. It's a walk. It doesn't go off the graph. It's a trail because it doesn't repeat any edges. It's a closed trail, which is also known as a circuit, and on top of that, it also visits every edge of the graph, which makes it an Euler circuit. Here are some helpful facts in applications of Euler circuits. First of all, Euler's theorem. A graph has an Euler circuit if and only if every vertex has even degree. Here's that graph that we found an Euler circuit for. Vertex E has degree 2 because two edges meet at E. Vertex D also has degree 2. Vertex C has degree 4. Vertex B has degree 2 and vertex A has degree 2. So all even degrees. However, this graph has lots of circuits, but not Euler circuits. So let's see what went wrong. So vertex F has degree 2, vertex G has degree 2, but vertex H has degree 3. Vertex I has degree 2, and vertex J has degree 3. So not all of the vertices have even degree. We have some odd degrees. That tells you that it can't possibly have an Euler circuit. However, a graph with odd vertices can be Eulerized. I know that's kind of a funny word. What do we mean by Eulerizing? What we do is we add some duplicate edges in order to force the graph to have all vertices of even degree. The resulting multigraph will have Euler circuits. First, we're going to identify the degrees of each of the vertices. So vertex A has degree 2, vertex B has degree 2, vertex C has degree 3, and vertex D has degree 1. So C and D have odd degree. If we add a duplicate edge between them, vertex C has degree 4, and vertex D has degree 2. So the resulting multigraph has Euler circuits, guaranteed. We're going to apply these concepts to a mail delivery application of Euler circuits. Consider the task of a mail carrier to deliver to every street in 2 neighborhoods and return to the post office, repeating the fewest roads possible in the process. The roads can be represented as edges in a connected graph, with vertices representing intersections. In our graph, vertex P represents the post office, which must deliver to every road. In order to find an optimal solution, we're first going to begin by analyzing the degrees of the vertices to determine if an Euler circuit even exists. Vertex P has degree 1, so this doesn't have an Euler circuit. But let's continue finding the degrees of all the vertices so that we can Eulerize it. Now we're going to go about the process of duplicating edges to create a multigraph that has an Euler circuit. So I'm going to start by duplicating the edge between P and F. That would mean that P now has degree 2 and F has degree 4. Now I'm going to look for two more vertices that are next to each other with odd degree, so E and A. So I duplicate that edge, and now they have even degrees. And then finally, we can also add an edge between D and G to change those from degree 3 to degree 4. So our new multigraph has all vertices of even degree. And now we're going to find an Euler circuit through the multigraph that we created, beginning and ending at vertex P, representing the post office. In this way, we can create a route for the mail carrier with the fewest repeated roads possible, because the only repeated roads will be those represented by the duplicate edges. Okay, so I'm going to begin by drawing a big old circuit. That just means I have to travel each edge only once and begin and end at the same place. So I'm going to go from P to F. There's no one right way to do this. F to E, E to A to D, back to C, back to B, back to F, and back to P. Now I'm going to start at any one of the vertices that I've already hit, and I'm going to create another circuit. The only rule is that I cannot cover any edges that were covered by the white circuit. So we're going to go from E to A to B, and B back to E. Ultimately, I'm going to replace E with this little circuit I just created that goes from E to A to B and back to E. But first, I still have some edges to cover. D is one of the vertices we visited the first time around. Let's start there for our next little circuit. So we'll go from D to G, then J, then I to H, then H back to G, and back to D. Instead of just stopping at D in our big long circuit, we're going to take a detour through the green circuit, then come back to the white. So ultimately, this is the circuit that we're going to have. We're going to go first from P to F, and then second we're going to go from F to E, represented here. And then we're going to divert to the blue. So we're going to go from E to A, and then from A to B, and then back to E. And that will take us through the blue, and then we're going to go back to the white. So then from E we're going to go to A, and then to D. That would be this piece right here. And then we're going to divert to the green. So we're going to go to D to G, and then to J, and then to I, and then to H, and then to G, and then back to D again. So that's all of this. And then we're going to go now join back up with the white circuit. So that's going to go from D to C, C to B, B to F, and then back to P. So we have this one big long circuit with a piece from the blue circuit plugged into the big long white circuit, and then also a piece from the green circuit plugged into it. So we found non-overlapping circuits and linked them together. An additional challenge to Eulerizing a graph and solving an application problem is that sometimes we're not lucky enough to have odd vertices that are conveniently positioned in adjacent pairs. Remember how the odd vertices conveniently were adjacent pairs, so we could just connect them? Then in each case we could change a pair of odd vertices into even vertices. Well, what if that's not the case? Let's look at this graph where we've got an additional edge between A and J. Okay, so we're going to imagine that our neighborhood has built an extra road with a row of houses on it, right? And now we have a vertex of degree 1, a vertex of degree 3, a vertex of degree 3, vertex of degree 4, 3, 2, 2, 3, 3, 2, and 4. Some of the odd vertices are adjacent to another odd vertex, like F and P here. Add a duplicate edge, and yay, this is now degree 4 and this is degree 2. But what can we do about vertex E? Vertex E is degree 3, but it's not adjacent to another odd vertex. Why can't we just connect vertex E to vertex D and make those two adjacent? That would imply our mail carrier is driving through everybody's backyard, right? So they're going off-roading. The mail carrier has to stick to the existing roads. The duplication of the edges is just to show that's where we have to backtrack. What we can do is connect E to a vertex of even degree that's next to another vertex of odd degree. One option would be to draw a duplicate edge between E and A. This would fix my problem with degree of E being 3 and change it to a 4. Unfortunately, that does change A to an odd degree now. But then we can fix that. A is adjacent to D, so I'm going to draw an edge between A and D. So now A has degree 6 and D has degree 4. And then luckily G and J, they are adjacent to each other. I can draw a duplicate edge between them, and now those have even degrees as well. This would allow us to find Euler circuits through the graph. Some experimentation may be needed to ensure that you are duplicating the fewest possible edges. I hope you found this video helpful. If you did, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Earn Mathematics, for more math videos.